All right, number 7. What would be the resulting volume of a 2.4-liter balloon at 32 degrees Celsius that was placed in a container of cold water at 2 degrees Celsius? Okay, so to do this problem, okay, you guys, a lot of you asked me, like, what's the first thing that you need to do to figure out what your formula is? Okay, so you look what you're given. You're given a volume and you're given a temperature. So then that's volume and temperature, that's Charles. Charles is very tall. So V1 over T1 equals V2 over T2. Okay, so when we look, our V1 is that first volume, which is 2.4 liters, and our T1 is that first temperature given to us, which is the 32 degrees. It is in Celsius, so we have to make sure that we convert it to Kelvin by adding 273. So this is 305 Kelvin. And then it says our resulting volume, so that means we're looking for our V2. So we need to be given our T2, which is 2 degrees Celsius. And then again, we're going to add 273 to make it our Kelvin temperature. Okay, so then we put our numbers in our formula. So 2.4 is our V1, 305 is our T1. That equals our V2, which is our unknown, over our T2, which is 275. And then from here, we cross multiply. Okay, so we take 2.4 times 275 equals 305 times V2. Okay, so on my calculator, I'm taking 2.4 times 275, and that is 660, and that equals our 305 times our V2 still. And then to get our V2 by itself, we divide both sides by 305. And they'll cancel out on this side, so 660 divided by 305 is 2.16 liters equals our V2. All right, next slide. Okay, number 8, a balloon has a volume of 18.9 liters at a pressure of 104.6 kPa. What will be the new volume when the pressure is 157.3 kPa? Okay, so we look at what we're given. We're given a volume and a pressure. So pressure and volume. So big purple van, that's our Boyle's law. So P1 times V1 equals P2 times V2. Okay, so our first volume is 18.9 liters. And our first pressure is 104.6 kPa. And it says what will be the new volume. So we're looking for V2 when our pressure is 157.3 kPa. All right, so P1, 104.6, times V1, which is 18.9, equals P2, which is 157.3, times our V2, which is our unknown variable. Okay, so my calculator, I'm taking 104.6 times 18.9, which gives us 1,976.94 equals 157.3 times V2. Okay, and then to get our V2 by itself, we divide both sides by 157.3, 157.3, and it cancels out on this side, and then we divide our other side. So 12.56, and since it's a volume, we look at our original unit, which was liters, equals our V2. All right, next one. A compressed gas cylinder has a pressure of 210 kPa at 40 degrees Celsius. The temperature of the room with the cylinder was increased to 45 degrees Celsius. What is the pressure now? Okay, so we have pressure and we have temperature. So pressure and temperature, kids love playing tennis, that's Gay-Lussac's law. So P1 over T1 equals P2 over T2. So P1 is 210. Our T1 is 40 degrees Celsius, and again we have to add our 273, which is, make sure I do it right, 273 plus 40 is 313 Kelvin. And then our P2 is what we don't know, and our T2 is 45 degrees Celsius. Again, we got to convert it to Kelvin by adding 273, and that gives us 318 Kelvin. Okay, so our P1 is 210, our T1 is 313, our P2 is our unknown, and our T2 is 318. Okay, so we cross multiply. So 210 times 318 equals 313 times P2. Okay, so on my calculator, 210 times 318 equals 66,780 equals 313 times my P2. And then to get my P2 by itself, I'm going to divide both sides by 313. Divide by 313, cancels out on this side. And I took this one, divided by that, and I get 213 kPa equals my P2. Okay. Next problem. I didn't really get a chance to talk about this in class, so I'm going to do it now. So if you're listening, you got this. Okay, so this is a heating curve of water, and this is a lab that we did the other day, and we didn't really get a chance to go over all the final things here, but we're going to. Okay, so this first section here, A, right here, you are heating your ice. So that means that all the energy that's from the hot plate is going into heating your ice. So that is heating your solids, so that is number 3 is A. Okay, then for B, right here, from here to here, all the energy that is being put into your ice is merely changing its phase. So at this point, all that's doing is changing phase. So it's going from a solid to a liquid. So that is the melting of the solid. So number 5 is B. Okay, then from here to here, you are now heating that liquid. Okay, you're now heating the liquid water because all of your solid has melted. So when you're heating the liquid, okay, we don't have that on here, but that's what C is. That's not any of the questions. Okay, so then we go. Then for section D, okay, at this time, all this energy is being put in to merely change phase. So the temperature doesn't go up, and you are just changing the phase. So at this point, you are boiling your liquid, okay? You're getting it to try to turn into that gas. So that is D, okay? And then at that point, your last little section is E, and that is when you're heating the vapor, because at this point, it's all water vapor, and you've turned it into gas. Okay, so if we go back to A, the melting point would be right here, which is 0 degrees Celsius. And then our boiling point is when it starts to turn into gas, which is right here, which is 100 degrees Celsius. All right. Okay, and then the last one, okay, arrangement of particles. Solids are touching. They're in an orderly pattern, okay, and they're closely touching. Their movement is very slow. They just vibrate in place. Definite shape, yes. And definite volume, yes. An example, any solid, you know, a desk, a chair, a car, you, any of those things. All right, a liquid, the particles are still touching each other, okay, but they are not in an orderly pattern, okay. Movement of particles is fast. They do not have a definite shape, but they do have a definite volume. You know, water is the easiest example for this. And then finally, gases, they're all over the place, okay, and they are not touching, okay. They only touch when they collide, and their particles are faster, okay, or very, very fast, whatever you want to do. And they do not have a definite shape, and they do not have a definite volume, and oxygen would be an example of this.